Welcome to this scientific lecture on one of the most fascinating frontiers in materials science, nanoarchitected metamaterial aerogels. These are materials that achieve extraordinary mechanical properties at densities lower than you might think possible. Let me start with a fundamental question. Can we create materials that are as light as air, yet as strong as metal? Traditional aerogels are among the lightest solid materials known, with densities as low as 3 milligrams per cc. However, they suffer from a critical limitation. They are extremely brittle and mechanically weak. The grand challenge is to combine ultra-low density with high mechanical performance. This is where nano-architected metamaterials come in. Compare a traditional aerogel with a nano-architected metamaterial. The metamaterial may be slightly denser, but its stiffness can be 500 times higher, and it can recover from large deformations. To understand why nanoarchitecture is revolutionary, we first need to understand classical scaling laws for cellular materials. The Gibson-Ashby model, developed in the 1980s, predicts the mechanical properties of foams and cellular solids based on their relative density. The relative density is defined as rho star over rho s, where rho star is the foam density and rho s is the solid material density. For open cell foams, the relative stiffness scales as the square of the relative density. E star over Es is proportional to rho star over rho s squared. This square scaling arises because the struts in the foam deform primarily by bending when the structure is loaded. Similarly, the relative strength scales as the 3/2 power of the relative density. Sigma star over sigma s is proportional to rho star over rho s to the 3/2. Let me give you a concrete example. Consider a foam with 1% relative density, so RHO star over RHOS equals 0.01. According to the Gibson-Ashby model, the stiffness would be about 1/10,000th of the solid material stiffness. If the solid material has a modulus of 100 gigapascals, the foam would have a modulus of only about 10 megapascals. This seems quite discouraging if we want to create ultralight yet stiff structures. The properties degrade rapidly as density decreases. But here is the key insight that revolutionized the field. We can design architectures where the load-bearing struts deform by stretching rather than bending. For stretching-dominated structures, the scaling laws are dramatically different and much more favorable. The relative stiffness now scales linearly with relative density. E star over Es is proportional to rho star over rho s to the first power. And the relative strength also scales linearly with relative density. This linear scaling represents the theoretical optimum for isotropic materials. It's the best you can possibly achieve. In a bending-dominated structure, horizontal struts bend significantly under vertical load. This bending is inefficient and leads to the unfavorable square scaling. In a stretching-dominated structure, such as an octet truss lattice, the struts are oriented so they stretch or compress axially under load. This is much more efficient. Examples of stretching-dominated topologies include octet truss lattices, kagome lattices, and various other truss-based designs. The question now becomes, can we fabricate these optimal architectures at the nanoscale? Advances in nanofabrication techniques, particularly two-photon lithography and atomic layer deposition, have made this possible. Two-photon lithography allows us to write three-dimensional structures with feature sizes down to 100 nanometers. Atomic layer deposition enables us to coat these structures with ceramic or metallic materials with nanometer scale thickness control. The fabrication process involves creating a polymer scaffold using two-photon lithography, coating it with ceramic via atomic layer deposition, and then removing the polymer to leave a hollow ceramic nanoarchitecture. Now let me address a crucial question. Why does the nanoscale matter? Why can't we just scale down macroscopic structures? Classical continuum mechanics treats materials as infinitely divisible. It assumes that material properties remain constant regardless of sample size. But at the nanoscale, this assumption breaks down. We enter a regime where size-dependent effects become dominant. One critical effect is flaw tolerance. Smaller samples statistically contain fewer critical flaws that can initiate fracture. According to fracture mechanics, the fracture strength is given by KIC times Y divided by the square root of pi times A, where A is the flaw size. When the sample size becomes smaller than the critical flaw size, there simply isn't room for a dangerous flaw to exist. The strength increases dramatically. For brittle materials, strength scales as d to the negative 1/2 power, where d is the characteristic dimension, but only when d is larger than a critical size dc. When d becomes smaller than dc, the strength approaches the theoretical strength of the material, which can be 10 to 100 times higher than bulk values. For example, alumina nanolattices with strut diameters of 50 nanometers exhibit strengths approaching 1 gigapascal compared to tens of megapascals for bulk porous alumina. Another critical consideration for ultralight structures is buckling. Slender struts can buckle before they yield or fracture. For a slender column, the critical buckling load is given by the Euler buckling equation. P critical equals pi squared times E times I divided by K L squared, where E is the elastic modulus, I is the second moment of area, K is the effective length factor, and L is the column length. For a circular cross-section, the second moment of area is pi d to the 4th power divided by 64, where d is the diameter. Therefore, the critical buckling load is proportional to E times d to the 4th power divided by L squared. The slenderness ratio, L over d, is critical. High slenderness ratios lead to buckling at low loads. Hierarchical porosity is a clever strategy to manage buckling while maintaining low density. With solid struts, buckling becomes a severe limitation when the slenderness ratio exceeds about 50. By making the struts hollow tubes, we maintain a high second moment of area while reducing mass. A hollow tube has much better buckling resistance per unit mass than a solid cylinder. For a hollow tube, the second moment of area is pi over 64 times the quantity d to the 4th minus d to the 4th, where d is the outer diameter and d is the inner diameter. For thin-walled tubes, we maximize the buckling resistance for a given amount of material. This is a fundamental principle in efficient structural design. Now let me address the most fascinating aspect. Why do classical scaling laws fail at the nanoscale? Classical Gibson-Ashby theory predicts specific power law exponents, 2 for bending-dominated stiffness, 1 for stretching-dominated stiffness. However, experimental data on nanoarchitected materials shows systematic deviations from these predictions, especially at very low densities. We can write E star over ES equals C times RAR HO star over RAR HO S to the power n, where C is a constant and n is the scaling exponent. For many nanolattices, the measured exponent n is less than the classical prediction. This means they perform better than expected. There are 3 main reasons why classical scaling breaks down at the nanoscale. First, the material properties themselves become size-dependent. The modulus ES and strength sigma S in the nanoscale can be higher than bulk values. Second, surface effects become dominant. At the nanoscale, the surface area-to-volume ratio is enormous. Surface stresses and surface elasticity can significantly affect mechanical response. The surface-to-volume ratio scales as 1 over d. As d decreases to nanometers, surface effects become increasingly important. Third, for metallic nanolattices, dislocation behavior becomes size-dependent. In nanoscale structures, dislocations can easily escape to surfaces, leading to higher strength. The combined result of these effects is that nano-architected materials can achieve specific properties that exceed classical predictions. Let me walk through a quantitative example to make this concrete. Consider an alumina nanolattice fabricated by atomic layer deposition on a polymer template. Bulk polycrystalline alumina has a Young's modulus of about 170 gigapascals. The density of bulk alumina is 3.95 grams per cc. Now consider a nanolattice with the following parameters. The unit cell size is 10 micrometers. The strut diameter is 100 nanometers. The alumina shell thickness is 10 nanometers. This geometry results in a lattice density of approximately 15 milligrams per cc. The relative density is about 0.0038, or about 0.4%. According to classical theory with linear scaling, we would predict E star would be 170 gigapascals times 0.0038, which equals about 650 megapascals. However, the actual measured modulus for such nanolattices is often around 1 gigapascal or higher. This is about 1.5 times higher than the classical prediction, showing the benefit of nanoscale size effects. Let me conclude by discussing the broader implications and future directions of this field. Nanoarchitected metamaterials represent a new paradigm for ultra-efficient structural materials. They approach theoretical limits of specific stiffness and strength. On an Ashby plot of stiffness versus density, nanoarchitected materials are pushing into previously unoccupied territory. On this conceptual Ashby plot, nanolattices occupy a unique space, low density like foams, but stiffness approaching polymers or even light metals. Many nanolattices exhibit remarkable recoverability. They can sustain compressive strains of 50% or more and fully recover their shape. This is completely unlike traditional ceramics, which fracture at strains of less than 1%. The nanoscale architecture enables pseudoductile behavior in inherently brittle materials. This recoverability makes them excellent candidates for energy absorption applications, such as protective equipment or reusable impact dampers. Beyond mechanics, nanoarchitected materials enable multifunctionality. The high surface area and controlled porosity allow for catalysis, sensing, and thermal management. For example, we can design thermal metamaterials with ultra-low thermal conductivity by optimizing the phonon scattering at nanoscale interfaces. The effective thermal conductivity depends not only on relative density, but also on strut diameter d and mean free path lambda of the heat carriers. Of course, significant challenges remain. Two-photon lithography is slow and expensive, limiting fabrication to small samples. Researchers are exploring alternative approaches including self-assembly, templating, and scalable printing methods to make these materials practical for larger applications. Let me pose a final question. What are the ultimate limits of mechanical performance at low density? The Hashine-Strickman bounds provide theoretical upper limits for composite material properties. For a two-phase composite of solid and void, the upper bound on relative stiffness equals the volume fraction phi of the solid phase. Stretching-dominated nanolattices approach this theoretical limit, especially when size effects enhance the base material properties. An exciting question is, can we exceed these bounds using active materials, field-responsive elements, or non-equilibrium structures? This remains an open frontier. Let me summarize the key scientific insights from this lecture. First, architecture fundamentally determines mechanical scaling laws. Stretching-dominated designs vastly outperform bending-dominated ones. Second, the nanoscale confers intrinsic advantages through size-dependent strength, flaw tolerance, and surface effects. Third, classical continuum mechanics breaks down when feature sizes approach 100 nanometers. New physics governs material behavior. Fourth, hierarchical porosity, such as hollow struts, optimizes buckling resistance per unit mass. Fifth, nanoarchitected lattices can exceed classical scaling law predictions, achieving superior specific properties. Finally, these materials enable access to previously inaccessible regimes of the stiffness density property space, opening new possibilities for ultralight structures. Nanoarchitected metamaterial aerogels represent a beautiful convergence of materials, science, mechanics, and nanofabrication. By rationally designing structure at multiple length scales, we can approach theoretical performance limits and even discover new emergent behaviors. The future of advanced materials is hierarchical, multifunctional, and rooted in nanoscale precision. We are just beginning to explore what is possible.